Yes.
Okay. Okay, so good afternoon, everyone. My name is Jin-Hyuk Kim from the South Korea. Now I'm staying in CSUB as a visiting scholar. I am currently principal researcher at Korea Institute of Industrial Technology. And also I'm associate professor at the University of Science and Technology Korea. Today, I would like to introduce the recent research trend of the hydraulic machines in Korea. Before starting my presentation, I'm highly thankful to Professor Jane for organizing this lecture and also to give a chance for presenting my research topic at this time. Also, I would like to thank all members for attending this time. So before starting my presentation, I would like to show the animation for introducing Korea Institute of Industrial Technology. This animation is about the 5 minutes. So now I will start now.
What we expect is beyond what we can see, turning ideas into technologies and turning technologies into reality. We dream of future-oriented technologies. We are pushing the limits of production technology, the boundaries of the manufacturing industry, and beyond the carbon economy, leading the manufacturing paradigm shift with new values. Korea Institute of Industrial Technology is an innovator of industrial technology. Amid the rapidly changing paradigm shift in manufacturing, Tech has grown to become a global partner in the innovative growth of the domestic manufacturing industry by developing technologies for autonomous manufacturing, servitization, carbon neutrality, and hydrogen alliance. We are redefining the productivity revolution to lead the value revolution in manufacturing. Beyond automation, we enable flexible and rapid production with autonomous systems and design optimized processes with digital twins to increase business competitiveness. We incorporate cutting-edge robotics and manufacturing technologies to create safe and reliable industrial environments. We're expanding business models by adding value to the manufacturing industry. We developed SMILE production technologies to help manufacturers enhance their R&D and design competencies and expand related services such as distribution and sales to generate high added value profits.
There's no voice.
We develop low carbon emission control technologies and industrial environmental management technologies through field demonstrations across various industries and sectors. Our research capabilities span the entire hydrogen energy cycle, including production, storage, transportation, and utilization. We seek to build a sustainable future driven by the carbon neutrality and hydrogen alliance in response to global climate change. We enhance the global competitiveness of Korean manufacturing through strategic global collaborations. We are transforming the future of industrial technology by expanding joint research and human resource exchanges with overseas offices, as well as strengthening the link to commercialization through technology transfer and infrastructure development. We will accelerate the implementation of autonomous production systems by conducting joint research with leading technology countries, preparing for a sustainable future by developing integrated hydrogen and carbon system technologies. Also, we contribute to the creation of industrial and innovation ecosystems by supporting domestic small and medium-sized manufacturers' global expansion and promoting industrial technology innovation for local manufacturing. The future is shaped by many technologies, but our path is singular. A path that transforms ideas into technologies and technologies into reality. A path leading from traditional manufacturing to an era of unprecedented value creation. At the forefront of this journey, Key Tech will advance beyond production towards true value. Korea Institute of Industrial Technology.
So, okay, so this is very interesting animation because we recently updated this animation. So anyway, so Korea Institute of Industrial Technology is South Korean government research institute to support advanced technology for the domestic and industry in Korea. So also actually Key Tech is mainly focused on the development and management of the manufacturing technologies for the small, medium enterprise in Korea. So now we have also branched for at the Silicon Valley in San Francisco. So we are always welcome to collaborate with the research work together. So, anyway, so now I'm just asking you then, what is turbo machinery? So we can say the turbo machinery is the rotating machinery like the fan, compressor, pump, turbine, and gas turbine, and so on. So anyway, so Wikipedia is defining the turbo machinery describes machines that transfer energy between rotor and fluid, including the both turbine and compressors. So why turbine transfers energy from the fluid to rotor, compressor or fan transfer energy from the rotor to fluid. So now I'm very interested in for both turbine and compressors, pumps, anything. So in this lecture, I will introduce briefly how can we design this type of machine or to improve the performance. So CFD means the computational fluid dynamics. So which is the small section of the fluid dynamics in mechanical engineering part. However, recently with developing the computing power system, CFD is also rapidly increasing to solve the fluid mechanic problem in detail. So also CFD can replace the directly experimental test to design initial model or optimum model more in detail right here. So also do you hear me my voice? Okay, so I will do next slide. So if we use the CFD, then we can design all kinds of turbo machinery like the fan, compressor, pumps, hydraulic turbine, pump turbine, because we can understand easily the internal flow characteristics by using the CFD techniques. So also there are so many types for the turbo machine, like the centrifugal type and the axial flow type and the regenerative type and the mixed flow type and so on. So they are employing to operate the best performance with the various types at the requested field. So this is the introduction. So actually I have professional skills and work capabilities for the fluid machinery like the fan, compressor, pumps, hydraulic turbine, and pump turbines. I'm also very interested to investigate the internal flow characteristics and the flow physics by using the unsteady CFD techniques. Also, I'm very interested to analyze the performance and so on. So by using the flow visualization. So I have also practical hands-on experience for energy machinery with the experimental and analytical investigations. I have performed successfully more than 34 research projects, and I'm doing now the 2 research projects as the principal investigator. Till now, I have also published more than 120 technical journals and also published more than 75 patents on kinds of the energy system. So currently, I'm doing 2 research projects funded by Korea government as the local PI. So you can check on the main keyword for developing the high efficiency industrial fan and the large size bombs. So in the first project, I brought small research items to do work at CSUB. Now I'm doing research work together with the Dr. Kyung-Sung Kim, who is a faculty member at the Department of Physics and Engineering, to investigate the unsteady stall characteristics analysis based of the variable speed electronically commutated fan by using the LES large eddy simulation techniques. So also in the second project, I brought also small research work for investigating the cavitation flow analysis of actual flow bombs by using unsteady large eddy simulation techniques. So I'm very interested in development of various fluid machines using experimental and CFD method combined with design optimization techniques. So you can see my research field for the fluid machinery, aero and hydrodynamic and aeroacoustic designs for the compressor, fan, pumps, hydraulic turbine, and pump turbine unit based on the unsteady flow visualization and the experimental techniques, and also the advanced statistical optimization techniques. So this is the next major researches. So just now I'm trying to develop the various bomb types for the single channel bombs, two vane bombs, also actual bombs, and so on. Especially almost bombs are already commercialized in Korea now. So recently also we have also constructed the experimental test facility to investigate the interflow characteristics and the physics mechanism more in detail. And also recently we have captured the cavitation phenomena as shown in here. And also we are analyzing more in detail using the unsteady CFD techniques. So since we got a good result, so recently we have published some paper at the Physics of Fluid. So you can see our affiliations in the CSUB at here. So this paper was published in July this year. So also this is one of my research item. So I'm trying the aerodynamic machines for the compressors used for the vacuum cleaner and the gas turbine system. But I will skip in this part because of the limited time now. So you can see here, this is also one of my ongoing research work for designing the hydraulic turbine with the very low head condition. So if we use the only kinetic energies, then we cannot get more power because of the batch limit law, which is one of the basic theory in this fluid machine. So however, if we use both the kinetic and potential energy turbine right here, then we can get more power. So recently we have installed the gate right here for making the artificial head. Then we can make the potential energy also. So recently we have completed the experimental test right here. Finally, we got a 30 kilowatt power from this turbine at this rear site right here. So recently we have also published some papers at the Energy and the Helion journal. So if you are interested in this work, then you can download freely in website. So anyway, so now I will talk about the single channel bump because this bump is very unique bump and this is very interesting topic. So I will show you briefly now. Actually, general submerged pump for wastewater treatment can be treated various wastewaters from the industrial and living sewage. However, existing braid type pump has many problems, especially the breakage and breakdown because of the clogging phenomena. So if we meet the problems with the clogging occurrence, then pump efficiency firstly decreased with the motor load and impeller operation and pump damage right here. So this is almost 98% for the breakdown of this pump. Then how can we do to prevent clogging problem in the pump? Then firstly, we can consider to increase the impeller size. So if we increase the impeller size, then we can meet also space limitation. And also pump input power also increased, and then also cost will be also increased. Then we can consider to install the grinder in front of pump inlet. Then this is also some problem because of the clogging at the suction with grinder blade operation. So we can think to use the multi-vane impeller. However, if we use the multi-vane impeller, then we cannot secure the flow path because we have to send the solid metals from this pump. So if we use the vortex pump right here, and then even though we can secure the flow path, however, pump efficiency is decreased because of the small impeller. So we have to develop the single channel pump for increasing the higher efficiency and to send solid metals smoothly. So this is the design theory for the single channel impeller and the volute based on the Stepanov theory, which is also one of the basic theory for designing fluid machinery. At this time, I have invented also the design method for the cross-sectional area shape and the distribution for designing the high efficiency model right here. So we can think about the also optimization procedure to improve this performance for this pump. So firstly, we can define the problems, for example, the geometry generation and grid dependency test and performance validation. Also, we can choose the objective functions, but in this work, so we have to increase it simultaneously to high hydraulic efficiency and to also reduce the fluid-induced vibration because this pump has the non-symmetrical impeller shape. So non-symmetrical impeller shape is rotating, then we can meet the very big fluid-induced vibration. So we have chosen the three design objective functions right here, which are the hydraulic efficiency and the sweep area of radial force during one revolution right here, and also distance between the origin and center point. So if we minimize the two objective functions right here, then we can reduce the directly fluid-induced vibration by the rotor-stator interaction. And also we can choose the design variable right here. At this time, I have chosen 5 design variables for changing smoothly the cross-sectional area distribution for both impeller and volute by using the Bezier curve. So, and then we can employ the Latin hypercube sampling method, which is one of the design of experience to make the combined design point. And then also we can start the calculation for getting the objective function values from the numerical result. And then also we can employ the multi-objective genetic algorithm combined with the surrogate modeling for getting the final optimal Pareto optimal front right here. So this is our optimization result. So you can see here, these are all optimization results. So we can choose the arbitrary several models for analyzing more in detail the trade-off relationship. So you can see these figures. So this is the unsteady pressure distribution at boundary surface of the impeller outlet. So as you can see here, reference model is changed rapidly unsteady pressure distribution with rotating impeller right here. However, this is the clustered optimal design A, so has almost uniform flows. Then we can think to reduce the fluid-induced vibration by the rotor stator interactions through the optimization techniques. Also, this is the radial force source distribution. So you can see here. So COD-A model is decreased considerably right here. And then also radial force is rotating almost near the origin of this graph. So also this is the also unsteady radial force fluctuations during the one revolution of the impeller. So you can see here, COD-A model has almost a uniform shape right here. So also we have tried also the FFT analysis. FFT means the fast Fourier transform analysis. So you can see here almost amplitude and magnitude values at the first braid passing frequencies are reduced considerably or local points right here. So we can think to reduce perfectly the fluid-induced vibration. So before several years, I have published also book chapter about our new technologies. So the title is the state-of-the-art design techniques of the single-channel pump for wastewater treatment. So if you are interested in my new design technology, then maybe you can freely download it in website. Also, this is the structure drawings for manufacturing of the optimum model because we have to verify real performance for the commercialization. Also, this is the also three-dimensional modeling for the manufacturing of our final optimum model right here. So also this is the also structure analysis for manufacturing of the final optimum model. So rotor dynamic analysis is also very important because we have to decide the location of the bearing and also to decide the thickness for the shaft shape, shaft axis, also for also checking the also dangerous velocity zones. So this is our final manufacturing process for the optimum bump model. So this is our prototype model for the commercialization. So you can see these animations right here. So vibration was reduced remarkably right here. So wave surface is due to only the discharge flow rate from the outlet pipe right here. So we got a very good result also. We got also good found the very lower fluid-induced vibration model right here. Also, for clearly explaining now, so you can see here left animation. So if we do not consider our design techniques, then there are so many vibrations right here by the fluid-induced vibration due to the rotor stator interactions right here. However, if we consider our design techniques, then you can check. You can see here we got a very low fluid-induced vibration model right here. Also, we have also checked to send the wet tissue as the solid metals. So you can see here, wet tissue is also smoothly driven right here. So we already verified all performances tested. So before several years ago, so we have announced the media report and the newspapers in this achievement in Korea. So also now our pump is already commercialized in Korea, and there are so many using many field and many applications. And also, you know, the Jeju Island. Also in Jeju Island, also this pump is using popularly. Also, this is the another application because this single channel pump can be also applied to clear hazard with the golf ball in golf house, because you can see here, golf ball also can sand smoothly, right, from this bump right here. So you can see maybe golf ball is coming from the outlet right here. So there are so many applications. So also recently our bump is employing many golf houses in Korea now. So at this time, we got many good results from this research work. So we have published so many papers. So if you are interested in this research work, then maybe you can download it really in our previous published papers. Also, this is also ongoing work, because this pump also can be applied as the turbine. Because if we use this pump as turbine, then we can also get power from the wastewater with the solid metals. So this is also very popular, because recently some Japan company asked me for, is it possible to design or develop this single channel pump as turbine for wastewater treatment, for generating this turbine from the wastewater. So now we are researching together. So now I'm collaborating with also China and the USA. So recently we got a very good result. So recently we have submitted some journal papers right here. So you can see also check our affiliation in CSUB now right here. So now is the positive displacement turbine. So actually, you know, the winter season in Korea is really so cold. So we are using always indoor system as the Korean floor heating system. So there are several heating companies in Korea, and also they have also a district heating network. So district heating network as the summer grid with pipeline is used to transfer the heat source to of medium temperature hot water less than 120 Celsius degree. Due to pressure drop of fluid in district heating pipeline, fluid has also hot water different pressure difference depending on the distance. So in the district heating system, actually pressure differential control valve is very important, because to supply constant flow rate from hot water pressure difference, and also to protect the usual equipment like the heat exchanger from the high pressurized fluid. Also to regulate the pressure at each point so that fluid can be supplied remotely right here. So recently, district heating company has investigated main equipment right here. However, you can see here, PDCV means the pressure differential control valve has broken by 14% every year. First of all, they bought always PDCV from the overseas. So this is the a schematic diagram for the pipeline and the pressure control valve in the heating system. So high pressure is coming here, and then pressure differential control valve and the temperature control valve can be control the pressure level to send the heat exchanger to exchange heat source to provide the users. And then lower pressure is returning the heating system at here. Then we don't move to these control valves. We can install the bypass line at here to install the hydraulic turbine to control the pressure level. So if we use the hydraulic power generation system in this site, then firstly we can get the some power from the pressure level. So we can supply the power to user, and also we can save energy storage. So hydraulic turbine system is suitable for the replacement of the positive pressure differential control valve in district heating substation. So there are so many advantages. For example, so if we use the hydraulic turbine system, then firstly we can control the pressure and also temperature and also to supply the bump inverter to send the power. So also this is most important for measuring the flow rate, because you know the this heating district system, there are so very complicated conditions, because they need to very hot water, and also very high pressure and very low flow rate. So this is very complicated conditions. So if we install the flow meter for checking the flow rate, then maybe flow meter will be broken. So we have to check the flow rate efficiently by using the hydraulic turbine system. So just now I will introduce briefly now. So this is the specific speed. When we check the specifications for designing hydraulic turbine, then firstly we have to check the specific speed, because specific speed can decide the turbine shape or turbine type. So if the specific speed is so big, then we can choose the actual flow type. However, if specific speed is very low, then we have to choose the gear type. However, as I told you previously, this condition has so complicated conditions. So specific speed is so low because high pressure and the lower flow rate are required this condition. So we have to choose the gear type for designing this turbine. So this is the initial design concept. So I have made design program by using Excel for roughly design the this turbine gear type shape. So also this is the three-dimensional shape. I designed the rotor lobe type shape right here. So I generated mesh for calculation by using CFD, and then also at the time I have employed the moving mesh techniques. So this is the example for our result. So you can see here, high pressure is coming here, then two rotors can be rotated by the high pressure, and then two rotors can get some energy. And then also low pressure is going outside from the outlet right here. But they are very interesting. So you can see here, there are very big separation zones at the outlet here. So these separation zones have adverse effect for the adverse effect on the performance of this turbine. So we have to reduce the these adverse effect for improving the turbine performance. So when we check the result for this reference turbine, so there are big pressure fluctuations right here. So this is the pressure fluctuations at the inlet and outlet, because you know this turbine shape is based on the rotor lobe type and the straight type. And then when we see from the outlet, then always changes the area. And then maybe we can make the very higher pressure fluctuation. Then how can we do or reduce the fluctuations from this turbine? Then we can try the two parametric study with the twisted angle from the 15 to 60 degree right here. So you know the screw type shape. So if we use the twisted angle model for this turbine, then we can decrease the considerably right here, the pressure fluctuations right here. So especially a 45 twisted model can be reduced perfectly right here. Also, this is the example for the result of the flow characteristics. So you can see here, if we use the 45 twisted rotor shape, and then when we see from the outlet, and then area is almost the same with the rotating of the lobe. And then also pressure fluctuation can be also reduced perfectly like here. So this is very simple idea. Also, we checked also the effect on the state shape because previously you checked the two separation zones from the outlet. So when we employ the rectangular diffusing type from the inlet to outlet, then maybe you can see this graph. So we can reduce the initial pressure pulsation right here. So you can see the rectangular shape right here. So finally, we can choose the rectangular diffuser shape for the state shape. Also, we have also checked the internal flow characteristics right here. This is the example. So you can see here two separation zones were reduced considerably compared to a previous model right here. Also, we checked also the effect on the clearance size because clearance size is very important for checking the turbine performance. And also, we are handling the hot water, so we have to also consider the heat expansion rate for both the rotor shape and also casing shape because two shapes are different materials. So we have to also check the clearance shape, clearance size. So anyway, so this is the example for the different clearance size. So also we have to also check the also cavitation performance because cavitation performance is also very important for working in the future. So however, if we use the twisted 45 design model, then we can clearly suppress the cavitation problem right here. So this is the also schematic diagram for the experimental test. So this is the main tank. In this tank, I have installed the also heater to increase the temperature. And also this is the booster pump for the making the artificial head. Also, this is the two reservoirs. This is the our prototype model. So we can also install the pressure and temperature sensors from the inlet to outlet for checking the some parameters. And also this is our turbine, and we can install the RPM sensor and torque sensor to check the exactly the turbine output. And this is the generator, and we install the also load bank for checking the for control the power by using the many resistance. Also, this is the magnetic flow meter to measure the flow meter, and also we can also install the heat exchange reservoir to control the temperature inside because this is the closed loop system. So when we do experimental test with long time, then maybe temperature will be increased. Then we have to control by using the heat exchange reservoir right here. So I have manufactured all devices right here in my institute. So I have tried the experimental test exactly. So at this time, so all devices were calibrated to get the accurate data right here. So this is our final prototype model. So you can see here, so high pressure is coming here, then two rotors can be rotated from the high pressurized rate right here. And then we can check clearly the some parameters from the all devices. And then finally, we have chosen the 45 twisted model right here. Also, this is our validation results. So you can see here. So our CFD results are very good agreement compared to experimental test data. So our CFD techniques is very reliable and very accurable data. So we can think. So this is also vibration result right here. So you can see here. So when we apply the 45 twisted model, then we can reduce perfectly the vibration right here. So you can see you can compare the amount to 0.5 and 20 millimeter per second compared to the straight to lobe type. So finally, so we can get very accurate flow rate from the below defined empirical correlation developed by the Buckingham Pi theory. So without the flow meter, we can get exactly the flow rate by using the empirical correlation right here. So also this is the performance curve map with the different temperatures. So you can see here, finally, we can develop the empirical correlation right here. So we can predict clearly the flow rate by using this turbine. So now we are trying the real field test to check the durability and also reliability now right here. So at that time, I have collaborated with Germany company, which name is the CFX Berlin. At that time, they have provided the Fortran code for generating the moving mesh of the lobe type shape right here. So also they also announced our achievement in their blog and homepage right here, so you can refer. And also one of my PhD students got a PhD thesis, PhD degree from these works. So at the time, we have published so many papers, so you can refer these papers. So this is the process turbine. So actually, hydropower plants play a vital role in electricity generation, which is the 16% of the worldwide power generation. Actually, hydropower plant has many advantages for sustainability and storage reliability and nature friendliness and flexibility. So you check also the Hoover Dam near here because this is also similar hydropower plant right here. So high pressurized flow is coming here, then they can rotate the runner, and the runner is directly connected in generator, and then we can get some energy from the power right here. So this is the hydropower plant in Korea. So capacity is about 45 megawatt. So at this time, so we have designed nearly the only runner and generator. This is the schematic diagram I will skip this one. So at this time, so we did not get any information because actually this turbine system was manufactured before 70 years ago. So we had no information data. So at this time, so we have tried the 3D scan for getting some information. So we got some 3D modeling here. So we made perfectly the 3D modeling geometry for the CFD techniques. So this is the computational grid for the CFD techniques. It was a really beautiful grid system right here. However, so for checking the numerical accuracy, so Professor Battaglia, who is the editor of the Journal of Fluid Engineering, she recommended to use the grid converged index method as the editorial policy of the Journal of Fluid Engineering. So at this time, we have tried the grid convergent index method for getting the number of optimal grid right here. So we have tested the validation because we have to verify our numerical result for the reliability right here. But our numerical result is very good of the month compared to experimental test data right here. Also, at this time, our mission was to investigate the unsteady cavitation characteristics with installing by the anti-cavity fringe at the direct tube right here. So we have employed the long fringe and short fringe and without fringe on the direct tube walls for checking the cavitation problem. So when we tried the unsteady simulation right here, so you can see here. So when we install the long fringe, and then we can considerably suppress the vortex cavitation loop right here compared to reference without shape right here. So for checking the clearancely, right here, so if we install the long fringe right here, and then we can reduce clearly the vortex cavitation loop right here compared to without fringe. So also we have also tried to check the internal flow characteristics, also the some frequency characteristics. So as you can see here, less than one frequency is almost occurred by the vortex cavitation loop. So, but if we employ the long fins, then we can reduce the by the 60% compared to without long fins. So we can considerably the suppress the vortex cavitation. So this is the our experimental test facility in K-Water Institute in Korea. So you can see here, so we manufacture the small scale for getting the some information from this test facility right here. So we have installed also many cameras for capturing the flow motion. So this is the example for the unsteady bubble formulation. So you can see here, so we got captured our numerical result, the bubble, unsteady bubble formation right here. So we have validated right here. Also, there are also some small cavitation is formed near the fin, near fin right here. Our also numerical results also captured very well compared to the experimental test data right here. Also, this is the real full cavitation result. So you can see here our numerical results also can capture very well, like the cavitation vortex phenomena right here. So also from this work, so we have published so many papers. So if you are interested more in detail our research work, then maybe you can check the, you can download our papers. So this is the bump turbine. So this is the our last model. So actually pumped storage generally operate by transferring water from the lower to upper reservoir using the idle power in pump mode during the light load times. After saving energy, discharging water in turbine mode during peak load time. However, recently, pumped storage is openly used to provide the stable power supply with the constant frequency for responding to fluctuations in renewable energy sources, such as the solar and wind power, which has been the increasingly added to grid over the last several decades. So also in this pump turbine, it's very important to investigate also the cavitation problem because they are operating many operating points, then they can meet frequently the cavitation problem. So it's very important to also check the cavitation more in detail. So this is our real pump turbine unit in Korea. Capacity is about the 400 megawatt in Korea. Now this pump turbine is operating in this now in Korea. So we also have validated to check the reliability for our numerical result. But you can see here, validation results are very good agreement right here. Also, we have checked also the cavitation characteristics by using the different flow rate. So for example, so in this guide vane angle 11 degree, then you can see here, cavitation is formed along with the blade shape. However, so for example, in guide vane angle 7 degree right here, then cavitation is formed like eddy type. So also we have tried also the velocity triangle analysis because this is also very important for designing the also pump turbine system, including the all turbine system. So you can see here, so there are big different cavitation characteristics. So for example, so in guide vane 11 degree, as right here, there are two separation zones right here. However, in this guide vane angle, 12.5 degree, then you can see here, very big unsteady cavitation loop is operating right here. Then maybe there are so big vibration and big breakdown. So we have to be careful. So this is the interpolated vortex characteristics right here. So you can see here there are big different type for the eddy type and the along with the shape right here. So I have also manufactured the lab scale model for checking more in detail the internal flow characteristics of the cavitation problem right here. At that time, I have installed the also 6 unsteady pressure sensors to check the more in detail the transient region simultaneously with the performance. So this is our experimental test facility right here. So at this time, I have also installed the also high-speed camera to capture simultaneously the flow motion. And all devices are synchronized to capture these all performances for the analysis more in detail. So this is the result of the hydraulic performances right here. We also analyze more in detail the frequency test results right here. So we also checked the vortex loop phenomena during the revolution at the different cavitation number. But you can check this one. We have captured very well the cavitation phenomena right here, but we have also our CFD techniques also captured very well right here. So from this work, so we can analyze more in detail by using the CFD techniques. So there are also 2 vortex loop right here, but just now this is our ongoing research work. So now we are analyzing more in detail the with another conditions for the turbine test, and then also we are trying analyzing and also by using the CFD techniques. So at this time also we have published many papers. So if you are interested in our work, then maybe you can check our papers. So this is my last slide right here. So now we are using currently a summer power plant as the base load. And recently we are using the solar and the wind energies as the renewable energies. Actually, renewable energy is providing the electronic power intermittently, and then quality is not so good. So if we combine the renewable energy and also pumped storage system as the backup device, then we can provide the suitable energy efficiently. So this is our final future energy system. So just now, I would like to finish my presentation. So thank you for your attention.
Thank you very much, Dr. Kim. This is very informative. So I want to say how, maybe the audience have some questions, but I do see a very interesting question on the Padlet. So one question is, why did you choose CSU Bakersfield as a site for your visiting scholar work?
Yes, thank you for your nice question. Actually, as I know, Bakersfield industry is mainly focused on the agriculture and also chemistry. So and then they need so many fluid machinery like the pumps. So at this time, I discussed with Dr. Kyung-Sung Kim. So he also need to develop the many type of bombs for application of the Bakersfield. So I chosen this region. So actually now I'm doing also my research project at here to develop the many kinds of bombs. So if I have a chance, then I will maybe discuss with some companies because in Bakersfield, there are many bomb companies. So maybe we can discuss to develop the commercialize also our bombs at here. So I have chosen at Bakersfield. Thank you.
Okay, great. So then, yes, we only have 2 minutes until the end of the session. I want to see if there's any questions from the audience at this point.
I do have a question,
Okay.
Dr. Kim. Thank you for their presentation. With all your work, do you have patents on any of your work at this point?
Sorry, what?
Have you patented any of your work? Yes.
Yes, I have so many patents, but I have only a local Korean patent. no without the international patent. But I have several international patent, but maybe we don't no problem to commercialize in the USA also. So there is no problem. So if I have a chance also to collaborate to research work with the CSUB, then we can also publish a patent together, and then there is no problem for the commercialization. Thank you.
Thank you.
That's fantastic. And also I see one comment on the Padlet to say that your technology also can handle the oil spill, right? That is a significant need in the Bakersfield, since we have a lot of oil and gas industry here.
Yes, I think so, right.
Okay.
Dr. Kim, I have a quick question for you. This is Danan Sani. So for your single channel pump, do you have any published data or from your previous research a comparison of the pump performance curve for this new design and a standard pump design?
Yes, of course. I have also published many papers, but
Yeah.
at that time, I have normalized all values, so I cannot announce my real performance test result. But if you want to get information, then I can send you privately.
Yeah, I was just curious, like based on the performance data. So it is like I believe it is comparable to the standard design, I believe.
Yeah, of course, yes.
Okay. Yeah,
Okay.
that's all I wanted to.
Okay, thank you.
Thank you.
Thank you so much, Dr. Kim. We would like to give you a round of applause. Okay, so
Thank you.
now let's end the session. By the way, the session is recorded, so the recorded basically video will be posted in the NSME website for everybody to review. So we hope you enjoy your visiting scholar experience here, and it's great to have international collaboration at NSME.
Thank you so much. Yes.
Okay, so everybody enjoy the rest of the day. Bye.
Thank you. Have a nice day.